So now let's look at the kinetic molecular theory and use these four different tenets to explain the macroscopic property of gases that we observe. Because gas molecules are moving constantly, and because the particles don't stick together, they move and fill up the containers they're in. In solids and liquids, the particles are attracted to one another and they stick together, and so therefore they have a limited volume that they'll occupy. Gases are compressible and have low density because of the large amount of unoccupied space between particles. Gases are mostly empty space, and therefore they can be compressed and have low densities. So here's a visual of gas atoms moving about, and because they're constantly moving, they're going to take up the whole container volume. And because they're mostly empty space, they can be compressed. Whereas liquids, the atoms or molecules are very close to one another. There's very little room for compression. The low density of gases is due to the fact that they are mostly empty space, and even though there is matter, it's very little matter for volume compared to solids and liquids. All gases have pressure, and pressure depends on several factors. The number of gas particles in a given volume, the volume of the container, and the average speed of the gas particles. So let's look at these two containers. They have the same volume. There are more gas molecules or atoms in this container, meaning there are more collisions against the surface of the container, meaning that the pressure is higher. If we decrease the volume of this, we would have more collisions in a given time against the surface of the container, and our pressure would go up. Or if we increase the volume, we would have fewer collisions, and the volume would go down. And if we increase the temperature, therefore increasing the speed of the gas, then we would also have higher pressure, because at higher temperature, gas molecules are moving on average more quickly, and therefore are going to strike the container surface more often, resulting in a higher pressure. So density and pressure are directly related for a gas. The lower the pressure, the lower the density. The higher the pressure, the higher the density. This is unlike solids and gases. Solids and gases do change densities according to temperature, but not by very much. There is a direct relationship in pressure and density for all gases. Now let's take a look at units. The units we're probably most familiar with are pounds per square inch. These are often the units that are used when we fill up our tires. Pound is actually a force. It's a measure of gravitational force. And square inch is the area. So we have the force per square area. And on average, atmospheric pressure is about 14.7 pounds per square inch. The Earth's atmosphere extends up about 370 miles, but 80% of the mass of the atmosphere is in the first 10 miles from Earth's surface. The average pressure of 14.7 pounds per square inch is the same pressure that a column of water would exert if it was about 30 feet high or 10.3 meters high. So a very, very high column of water, about 30 feet high, filled with water, would exert that much pressure on a square inch. How do we measure air pressure? Well, air pressure was first measured using a barometer, and here is an example of the first primitive barometer that was made. A tube was filled with mercury, and the tube was inverted into a pool of mercury. And the scientist who did work on this, Torricelli, noticed that this level would move up and down. And he theorized that it was air pressure that was pushing down on the mercury, and when the air pressure was equal with the force of gravity on the mercury, then that's where it stopped. And he was actually correct. This is actually now considered to be the correct explanation for this. So mercury is a very dense metal. It's very heavy in a small amount of volume, and it has a strong force of gravity pulling it down because of its mass. So therefore we don't need a 30-foot tube like we would with water. We only need one that is 760 millimeters or a little less than a meter. There's 1,000 millimeters in a meter. And air pressure was first measured by millimeters of mercury. How many millimeters of mercury on this barometer was the mercury pushed up? And we still use, in the United States, the unit of inches of mercury. The higher up in the atmosphere you go, the fewer gas particles there are, and therefore the lower the atmospheric pressure is around you. At the surface of the Earth, the atmospheric pressure is about 14.7 pounds per square inch. But if you go up 10,000 feet, it is only 10 pounds per square inch. Let's get rid of the second is. Rapid changes in atmospheric pressure may cause your ears to pop due to an imbalance in pressure on either side of your eardrum. So here's your eardrum. Here are the gas molecules. The blue represent the nitrogen, which makes up most of air. The red represent the oxygen. And so when there's a difference in pressure across the membrane, eardrum membrane, the membrane will be pushed out due to this extra pressure in here, and that's what we call a popped eardrum. Now let's take a look at the units of pressure. These are the conversion factors. This is the average air pressure at sea level given in these different units. And so let's look at atmosphere. We've already seen that 1 atmosphere is equal to 760 millimeters of mercury, is equal to 29.92 inches of mercury, is equal to 760 torr. So a millimeter of mercury and a torr, named after the scientist Torricelli, are equal to one another. And 1 atmosphere is equal to 14.7 pounds per square inch. The metric unit for unit is Pascal. 101,325 pascals is equal to 1 atmosphere. This is a rather large number, so often we use kilopascals. 101.325 kilopascals is equal to 1 atmosphere. So these are the relationships between these different units of pressure. There are many, many more, but these are the ones that are most typically used in chemistry. And you will be expected to use these to solve dimensional analysis problems. So here's an example. A high-performance road bicycle is inflated to a total of 125 pounds per square inch. What is the pressure in millimeters of mercury? So we want to write down what we're given. We're given 125 pounds per square inch. We want to write down what we want, our millimeters of mercury, and we look back at our table to get our conversion factor. 760 millimeters of mercury is equal to 14.7 pounds per square inch. And so when we set up our railroad math, we start off with our given, which is pounds per square inch. Pounds per square inch, therefore, in the denominator. The other half of our conversion factor is in the numerator. Our pounds per square inch cancel out. We're left with units of millimeters of mercury, and this is the value that your calculator should give you. Now let's look at sig figs. We have 3 sig figs to begin with. This is our last allowable sig fig right here. I'll look to the right, it's only 2, so 6.46 times 10 to the 3 millimeters of mercury. 760 and 14.7 are going to be considered exact numbers. So the last thing we want to do is make sure that our answer makes sense. 125 pounds per square inch, 6,460 millimeters of mercury. Yes, that makes sense because there are many, many more millimeters of mercury than there are pounds per square inch in this conversion factor. So we should have a higher number here, and we definitely do.